Now let's see some more properties of groups. Here's a theorem. And we assume G is a group, and let's say A and B are arbitrary elements of the group G. Then the inverse element of AB is B inverse times A inverse. Okay, what this means is that A and B are elements of the group, and AB is also an element of a group, right? So it should have its inverse, and that inverse is given by this in terms of B inverse and A inverse in this order. Okay, so let's prove this. Proof is actually easy. So B inverse A inverse times AB is, by associativity, we have this. So this first. And since A inverse is inverse of A, of course, that's the identity element. But identity element doesn't change anything, so either multiply here or here. In any case, we have this, and this is equal to E. So therefore, the inverse, B inverse times A inverse, is the inverse of AB. Right? Because if we multiply this to AB, we got the identity element, and we are done. And as a corollary to this theorem, we have this. If we have n elements from the group G, if all of these are elements of G, then the inverse of their product, A1 times A2 times and so on up to AN, the inverse of this element, this product, is AN inverse, AN minus 1 inverse, and so on, AN, A2 inverse, A1 inverse. So that is, it's the product of inverses starting from n to 1. Okay, and you can prove this in the same manner as this theorem. Or you can, of course, use mathematical induction. We have already seen that by writing a to the power of n for any element a of any group, and n is any natural number or 0, we mean okay, a to the power of 0 means the identity element, and a to the power of n is equal to a times and so on. That is, a appears n times, right? Now we want to define a similar notation for negative integer index. Okay, so here's the definition. For any element a of G and n in natural numbers, we define a to the power of negative n as a inverse to the power of n. Okay, so this is the definition. Now, together with the previous definition of powers, then we have a to the power of n for any integers, okay, including negative and positive and 0. Okay, now we can write like this. So if n happens to be negative, that means this. Okay, let's see a few simple examples. Let's say a to the power of 3 times a to the power of negative 2. So this means a to the power of 3 times a inverse to the power of 2, right, by definition. But that means we multiply a 3 times, and we multiply a inverse 2 times. But using associativity, a A inverse, A inverse. And this becomes identity. So we can just cancel it. And A times A times A inverse. Again, this is an identity, so we cancel it. And the result is A, which is, of course, A to the power of 1. And another example, A to the power of negative 3 times A to the power of 2. So that means we just skip some steps, and this means A inverse, A inverse, A inverse 3 times, and A times A. So using this times this is, so they can be cancelled, and these can be cancelled. The result is A negative, A inverse. So as you can see, these, A can be any element of any group, but they behave much like any numbers, right? So some number, so this is like exponential arithmetic. In fact, in general, we have this index law for groups. Uh, Let A be any element of a group G, then we have A to the power of m times A to the power of n is equal to A to the power of m plus n, where m and n are any integers. So they can be positive, negative, or 0. Okay, let's prove this. And when m and n are both non-negative, then we have done that before, so it should be okay. So if both m and n are non-negative, then already proved. So we have to consider 3 cases. So m is negative and n is non-negative. So 1 and 2, m is non-negative and n is negative. And when both are negative. Okay. And when n is equal to 0, then it's just multiplication by identity, so it's trivial. So let's assume n is positive. So we prove only for this case. Wait a minute. Let's prove for this case. Okay. So suppose m is positive and n is negative. Then let p equals to negative m. So this means p is positive, right? So a to the power of n times a to the power of n is a to the power of m times a to the power of negative p. Okay, but by definition of negative exponent, this is equal to a inverse to the power of p. Right? So just expand everything. We have a times, and so on. So a appears m times, and a inverse, and so on. A inverse that appears p times. Okay, then consider this and this element. So if we multiply this, that becomes identity matrix. So we can cancel this and this. So after this operation, we have m minus 1 a's and p minus 1 a inverses. Then we consider this a and this a inverse, and we can cancel this, and we can continue this process. So after all, the result would be either we have a, so that will be so m minus p a's, or p minus m a inverses, or E. So in this case, P is equal to M. So in this case, P is greater than M. This is M is greater than P. So there are three possibilities. So in either case, okay, let's see. So in this case, let's see, when P is less than M, so in this case we have a m times a n is equal to a m minus p, right? So that is a m plus n, because negative p is equal to n. And when p is greater than m, we have a m times a n is equal to a inverse p to the power of m. But by definition, this is equal to a minus p m, but that is equal to a m minus p, which is equal to a m plus n. And when p is equal to m, we have a m times a n equals to e, which is a to the power of 0, which is a m minus p, which is a m plus n. So in any case, we have the same result. That is the one we wanted to prove. So at least for this case, the statement is true, but we can prove in a similar manner for this and this. So you should try that. And we finish our proof. Let's see an example. Suppose we have three elements, x, y, z, in some group G. So let's simplify this product, yx inverse and yx inverse squared, xyz, and x negative 3 and y squared and z inverse. So let's call this element G. Okay. So for this one, we have, the inverse of a product is the product of inverses, where the order of product is reversed. So that's x inverse and y inverse. And this one, just write the same thing twice. Okay. We are not assuming commutativity of elements, so don't write yx this squared as y squared x negative 2. So this may not be true, because the commutativity may not hold. So for this, we have to write like this. Okay, so the same thing, the whole thing twice. And xyz, and for this one, inverse everything. So that is z inverse y to the power of negative 2 and x to the power of 3. Okay, so let's see. This part we can cancel y. And for this part we can cancel x. For this part we can cancel z. So let's cancel all of these. And wait a minute, where's y? Y inverse y, so they cancel. X inverse y, y, and y to the power of negative 2 x cubed. Okay, so here we can cancel these two, and we have x to the power of negative 2 x to the power of 3, and that is x. So that's it. We introduce some more terminology. Let's see, definition. And let's say we have two elements of a group G. So we say A and B commute if AB is equal to BA. Okay, in general, this may not hold, but if it does hold, then we say A and B commute. So this may hold for particular pair of elements. Okay, but if this commutativity holds for any pairs, then we say the group is abelian. Okay, the group G is abelian if for all pairs of elements of G we have AB equal to BA. So if all pairs commute, then the group is abelian. Or we say G is non-abelian if this is not true. If G is not abelian. So this, okay, not abelian does not mean that for all elements, for all pairs of elements, they do not commute. Okay, so negation of this statement is not that. The negation of this statement is that there exists some pair for which the commutativity does not hold. Okay, if there is at least one pair of elements that do not commute, then the group is non-abelian. Okay, or non-abelian we say non-commutative. Abelian we say commutative group. Non-commutative, commutative. Okay. And furthermore, if a group is abelian, we tend to write the binary operation as addition. Okay, if G is abelian, the binary operation, the binary operator, not always, but often, is often denoted as plus sign. Okay, so instead of writing AB, we write A plus B. Okay, and A plus B is equal to B plus A, and so on. Okay, let's see an example. So suppose for all elements of a group G, we have a squared is equal to the identity element. So this means for all elements, for every element, its inverse is itself. Okay, every element is the inverse of itself. Then, if that's the case, then the group is abelian. Let's try to prove this. Okay, since a squared is equal to e, then we have A inverse is A. Right? So every element is its own inverse. So by assumption, for every element A and B in G, we have AB is an element of G, so its square is E. Okay, so that means AB is equal to its inverse, but the inverse of a product is B inverse times A inverse. Okay, but B inverse is B itself. A inverse is A itself. So therefore AB is equal to BA for all pairs of AB. Therefore G is abelian. Let's see a few more examples. The first example, not Q, but O. Let's O of 2 denote the matrices of this form. Cosine theta, sine theta, negative sine theta, and cosine theta, where theta is a real number. So let's denote these matrices by this T theta as this. Okay, and we also consider as the binary operator the usual matrix multiplication. Okay, then this set O2 is a group. Let's see this. So let's see T phi times T phi is cosine theta, sine theta, negative sine theta, cosine theta. First, we want to see that this set is closed under matrix multiplication. Okay, so cosine phi, sine phi, negative sine phi, cosine phi. So if we multiply these matrices, we have cosine theta cosine phi minus sine theta sine phi, and cosine theta sine phi plus sine theta cosine phi, and negative sine theta cosine phi cos phi, and negative sine theta cosine phi minus cosine theta sine phi, and negative sine theta sine phi plus cosine theta cosine phi. And by using the trigonometric formulas, we see that this one is equal to cosine theta plus phi, and this one is sine theta plus phi, and this one is negative sine theta plus phi, and this one is cosine theta plus phi, which is t theta plus phi, which is an element of O2. Therefore, this set is closed under matrix multiplication. Okay? And associativity is trivial because it's based on matrix multiplication, which is associative. Okay? And what about the identity element? That is given by T0. That is cosine 0, sine 0, negative sine 0, and cosine 0, which is actually the identity matrix 1, 0, 0, 1. And also we have t negative theta is equal to, as we have seen in this, this is equal to t negative theta plus theta, which is t0, which is the identity matrix. So the inverse of t theta is t negative theta. So for each element of this set, we have its inverse within that set, right? So this also belongs to O2. So we have the identity element, inverse for every element. So therefore, this is a group. And also, since we have this t theta phi equals to t theta plus phi, but this is theta plus phi is just addition of real numbers, so this is commutative. So that's phi plus theta, which is t phi times t theta. Therefore, this is commutative for every pair of elements. So O2 is an abelian group. Okay, next example, let's consider a mapping parameterized by A and B from real numbers to real numbers. Okay, and this mapping is defined by this A plus bx, and A and B are parameters. Okay, then we have we can compose such functions fcd after fab is actually we have c plus ad and bd. Okay, and a, b, c, d are all real numbers. Okay. So to see this, we just apply the definition here. So cd after fab of x is, so this is function composition. So by definition, it is something like this: fcd of fab of x. Then apply the definition of this. We have fcd of a plus bx. Then apply the definition of fcd. Then c plus d times inside this a plus bx. So that is c plus d times a, which is equal to a times d, and plus b times d times x, which is f of c plus a d and b d, which is this of x. Okay, now Let's see, we have a set of such functions. Okay, where a and b are real numbers and b is non-zero. Okay, we impose this condition. Then T is a group. So T with function composition as the binary operator. Composition is a group. And to show this is a group, first you need to show that this set T is closed under function composition, which actually we have already done here. So if we compose two of these functions, the result is the function of the same form, but with different parameters. So it is closed, and associativity should be immediate because function composition is associative. And what about the identity? What's the identity element? So we need to show identity element, and we need to show the existence of inverse elements for each element. Okay. So for this case, the identity matrix would be, let's see, f of 0, 1, which has this form. So 0 plus 1 times x, which is just x. So this should act as the identity element for this group. And what about the inverse? Inverse will be, so if we have a, b, then what is this function? If this is the identity function, then this should be equal to this. Okay, so in that case, what is this function? So this should be equal to some function with some parameter. So what are these values, c and d? Okay, so let's find out. So if we compose, let's see. If we compose a, what was it? Let's try instead, not here, but here. Okay, so let's compose CD with after a, b, and for that we have this previous result, C plus AD and BD. So if this is to be equal to 0, 1, then we should have C plus AD equals to 0 and BD equals to 1. Okay, so given AB, what's the values of C and D? So from this, we have D is equal to 1 over B. Because we're assuming B is non-zero, so this is okay. And if that's given, then from here, C is equal to negative A D, but D is this, so negative A over B. So if we set C and D to these values, then we have the inverse function of this, which is negative A over B and 1 over B. So since B is non-zero, this is okay, well defined. So for every element, we have its inverse. Therefore, this set T under function composition is a group. Okay, the next example, let's set x equal to real numbers except for 0, and 1. Okay, then we define the following mappings on X. Okay, the first one is defined as this, so it's the identity function. And a of x is defined as x minus 1 over x. And b is defined as 1 over 1 minus x. And c, 1 minus x. And d, x over x minus 1. And f of x, 1 over x. Okay, so 1, 2, 3, 4, 5, 6. These 6 functions. So these functions under function composition makes a group. Okay, you should check. To check that, to check the closure condition, you should construct the Cayley table. So try to make this kind of table: A, B, C, D, F, E, A, B, C, D, F, 1, 2, 3, 4, 5, 6. Yeah. So try to compose all of these and fill in this table with one of these symbols. Then, all the results of multiplications should be one of these. Then you can check if you can check that, then you confirm that this is a group. Okay, let's try one example. So let's compose A and B. So A after B is this A of B of x, right? So B of x is 1 over 1 minus x. And if you apply this to A, and A is x minus 1, so that is, in this case, x is replaced with 1 over 1 minus x. So minus 1 over this argument. So that would be 1 minus x and 1, and that is x, which is e of x. So a times b is e, as it seems. A, B, C, D, F. So in this way, you can fill in all these cells and check whether this is indeed a group. Okay, next example. First, we set the set X as pairs of real numbers, X and T. Actually, this example is inspired by physics, classical physics. Then for each real number, V, we define the mapping from x to x as dv of xt equals to x minus vt and t. Okay, so this is so tv is a mapping parameterized by the real number v. Okay, then we define the set S as the set of all such transformations where v runs over the entire real numbers. Okay, then S, this set with function composition, is a group. Okay. So, by the way, this function is called Galilean transformation. So this transforms the space-time coordinates to the one that is on the with the velocity v. Okay. So to see this, to see that this is indeed a group, you need to show that the set is closed under function compositions. So let's say we have v and u. So this is a transformation. Let's say x and t. By the definition of function composition, we have this. And first apply tu. By that we have x minus ut t, and then apply tv, and we have what was that? So that would be x minus ut minus vt and t. Okay. Now we can factorize the first argument, x minus u plus vt and t. But this is transformation defined as u plus v of xt, which belongs to the set S. So this set is indeed closed under function composition. Then you can check associativity, which should be trivial because function composition is associative, and the existence of identity. What is the identity in this case? You should think about that. And what about the inverse of each element? Then if you check all of these, you can show that this is indeed a group.